All right, welcome back to part two of laws of thermodynamics. So basically, so far we just did a quick we did a quick video on the conservation of energy. So that was the first one we did, and we showed how this theoretical understanding of probability, which we're going to talk about today, how this can relate and give a line of reasoning towards the law of conservation of energy in that thermodynamic sense, talking about work done on a gas, talking about internal heat of a gas, and then the total system energy. So it gave us a couple definitions. We got this definition here: dq is equal to TdS. So we still don't even know what entropy is. We're going to discuss that today. And we also gained this definition over here for the average pressure, another quantity associated with the gas, and it has something to do with this free energy here, which has been rather mysterious so far. So before we go anywhere with those concepts and questions, I want to revisit probability. And if you've been watching along since the first video, it's probably become abundantly clear that we've done all these mathematical derivations but provided no sort of meaning as to what probability means. So what I'm going to do is I'm going to try to explain it by analogy. So yeah, let's jump right in. So let's assume, first of all, it's a two-dimensional system that I'm going to look at. And let's assume we have a box of particles. Okay. And for simplicity, let's just show that there's three bouncing around in here. All right. So there's three particles. And what can we say about the system? There's going to be some energy associated, and I'm going to call it energy I. And let's put another box next to it. And this is going to be a theoretical box. It's not physically located. These boxes are not located in space this way. I'm going to attempt to represent the same three particles with different configurations. And in our model, let's assume, for example, let's assume our energy function is very simply just a function of the kinetic energy. Okay, so let's assume it's just a function of the kinetic energy and there's no potential. So we're only looking at speed distributions here. So then maybe we can call this EI plus 1, the next container up, EI minus 1. And what we might observe about all these possible different configurations is that when you have continuously changing variables, like speed and momenta, for example, there are an infinite number of these boxes. If you really think about it, how many different variations of speed can you have? And there are infinitely many of them. This is not a statement about the reality of matter. Is matter on the infinitesimal scale? Is it discrete in nature? There are maybe some questions in physics about that, but I'm not attempting to answer that. So I'm going to let me try to organize these boxes. Of course, they're infinitely many, so it's a bit of a bizarre thing to do. We'll call this E0, and we will let that equal 0. And E0 being 0 means that, well, the three particles inside are not moving. There's no energy attributed by any of these three particles. Okay, and then on the opposite side, and this is not going to make any sense at all, let's call it En maybe, or En goes to infinity. And since there's no really any sensible way to draw this, I'm just going to draw some crazy lines coming out of this. There's infinite energy there somehow. So what we want to ask about is what is the relationship between this probability function and this collection of states that we've drawn? So, well, we know what the probability function looks like. And there's a few things that we can sort of observe before we even try to graph the probability function. First of all, what is Pn? What is the probability that the energy is infinite? I'm going to say it's 0 because I do not think that this is physically possible. So that's one statement I'm going to make. How about the probability of being in the ground state, P0? Well, I'm gonna really get into this one real soon, but I'm gonna show that this is actually a maximized probability. Okay, so in terms of the speed configuration, let's just move this out of the way. We know that that's true. In terms of the speed configuration purely of this guy, there is only one configuration of this box. Okay, there's only one. I don't care where these three particles are inside the box, as long as their speeds are 0, there's one configuration. If I look at what I'm going to call a column here, if we look at this column, how many different ways, and maybe I'll use a different color to try to clarify this a bit more. How many different ways can you organize this box EI, to get this same energy from those three particles? Well, if you really think about it, once again, a bit of a strange thought experiment, but there are infinitely many ways, actually, just even in its own, in this single energy level. So there's this sort of multiplicity of infinities happening here. The important, very, very important concept is that when you look at this thing, there's one state. There's exactly one state of these speed configurations that corresponds to energy being 0. And then as you ramp this up all the way over here, let's use pink. As you ramp this up, what we're going to say, the quantitative statement we're going to make, is that the number of states that you pack in gets higher and higher, so that when you get in here all the way up to infinity, the number of states, there's an enormous number of states with infinite energy. Actually, I don't even think there's any real way to quantify this. But the important thing is that the density of states that we're packing in is increasing. So we know what the function is. It's P is equal to some normalizing factor times e to the negative epsilon over kt. So we can graph this. It's not super straight. And we get a negative exponential. And at e equals 0, and we've shown this before, p at e equals 0 equals a. And it is indeed a maximum value. Okay, so far that checks out. Now, what do we mean as the energy increases, the probability is decreasing? What we mean by that is as you come across here, as you come across in these boxes which are ordered from 0 energy to infinite energy, the probability of any individual one of these states goes down because of their multiplicity. Okay, so because of the multiplicity of these states, right? Multiplicity of these states is causing the probability of any single one of these configurations that leads to energy state EI, that leads to EI, all of these lead to EI, it goes down. So this is the intuition for this formula, and then when you go out to infinity, it goes to 0, okay? So that is our understanding of probability and what it means for the system. You imagine this multiplicity of states, and we can see that as you order them from lowest energy to highest energy, this multiplicity massively explodes. And the probability of finding, in fact, maybe the only technical thing you can say about probability infinity is that the probability of finding any one of these states is 0. Okay, it's a bit of a bizarre thing, but imagine if you just had an ordered set of objects. Let's say you had all these objects. Well, what's the probability of picking up any one of them? In this case, it's going to be 1 over 5. As you get infinitely many of these objects, that probability diminishes. Okay, so that's probability. And that's where we're going to start with to talk about entropy. Entropy, which we've already defined, let's rewrite out the definition. S equals negative k ln p. Now this is a function of probability. So let's first graph, well, what's ln p, or k ln p, okay? What's k ln p? Well, entropy kind of does this sort of thing. I'll try to draw this. Now this is a monotonically increasing function, but here it's basically, this is 1. So at p equals 1, the function goes to 0. And so what we can do, I don't really care about probabilities more than 1, so when we graph negative k ln p, which is our entropy, is what we actually want, I'm going to flip this first half, okay, and sort of bring it down to 0. So what does this mean? Well, it means for increasing probability, our max, remember we had a p max, and our p max sort of, Sorry, went too far. Pmax is here. So we don't expect this P to go all the way to 1, actually. We expect the P to come up with some Pmax value. And what we notice is that this is obviously Pmax, but this, if you look this way, is S min. So what does this statement say? All right, it says that for the maximum probability, we have the lowest entropy. And this is the statement that we're trying to get to. And what does entropy have to do with the internal heat of the system? Well, for this system at absolute zero, this system here is absolute zero. Okay, what is the statement that we're trying to make about the internal energy? Well, at Pmax, we have the lowest entropy. Okay, so this is one statement that we can make about entropy. The opposite is also true. As this probability drops, okay, so as we get higher and higher energies, as we can see in our diagram here, the entropy will increase. The entropy will go up. So this is sort of law number 2. What is entropy? In talking about its existence. And sort of law 3 as well, because I've also talked about what happens at t equals 0. What I want to talk about quickly here, briefly, and we won't spend too much time on it because this is mostly a theoretical overview, but this chart, this graph, if you've noticed, has been ordered from order, what some might call order, to disorder. So a question is that why, or I'm going to pose it. I'm going to say we live in a universe where things seem to go from order to disorder. And I won't say that that's necessarily true. It's not that we're not going from no energy to some energy. This is the incorrect way to look at this. And I'm going to draw a quick diagram here. Imagine you have 2 boxes that are separate. Okay, we have box 1 and box 2. And box 1 has blue particles flying around, and box 2 will have orange particles flying around. I think with the definitions that we just gave for everything, we know that they will each have quantities of energy and entropy and temperature. Each individual box, maybe we'll call this 1 and we'll call this 2. The question is what happens when they combine, and what is the tendency of this system? What is the tendency of the system? And the answer we're going to give is one of probabilities is going to help us answer this. But what is the tendency of this system when you bring them together with a thermally transparent barrier? So let's assume for now these are still on this side. Let's call this T0. And then on the other side, the other particles are there. There's some very interesting things about Laplace's demon and some thought experiments you can do about information here. I'm going to talk about probability. Well, what happens when these become one system? Let's just use blue. Okay, when it becomes one box at some later t. Well, what you're going to see is that now all of these particles are in here. And the statement that I'm going to make, actually I'm not drawing this very well, these particles will mix. Okay, and these particles will mix. We know this from our intuition about how particles move. The billiard ball interactions inside here, right? They're gonna mix around. But the question is, what is the statement that we can make about entropy? Here we go. Let's get those last 3 particles in there. 1, 2, and 3. Okay. So what is the statement we can make about entropy of this guy? Well, there's one very important thing, and that is the number of configurations. The number of configurations is higher. Okay. So in our discussion before, as compared with the 2 initial systems, the number of speed configurations is now higher. Okay, and I don't know exactly how to explain that any better, but this happens when you have all these particles come inside this box. They have chances of colliding. There are now 6 particles inside the box. The space is bigger. There are a lot of, I guess, quantitative ways you could try to answer that question, but basically, in our discussion as per before, the number of configurations, these sets I was talking about, this ordered set of configurations is increasing. And because this ordered set is increasing, well, what happens to our probability? Our probability goes down, means our entropy goes up. So this is why over time systems have a tendency to increase in entropy. Okay guys, we're getting pretty long in the video, so I'm going to cut this one off here. This was basically what I had to say on entropy and probability and the laws of thermodynamics. So please like and comment and subscribe and just let me know what you think.